Until now, our OS was alive but a deaf. It could execute instruction, print text, and manage memory, but it could not react to the world. Today, we build the nervous system of our operating system. So, start with an example. Uh, Imagine your computer is a giant luxury hotel. Suppose here is a computer, giant luxury hotel, and the CPU is a general manager, and the keyboard is a guest, and timer is a hotel clock, and interrupts are the phone calls. The IDT is the hotel emergency contact book, and ISR handler are the staff teams. So this analogy basically comes directly from this page. It means normally, the CPU executes the code line by line. But what if a key is a press, a timer ticks, the disk finishes reading, the division by zero happen? The CPU cannot continuously check the everything manually. Okay, that would waste the enormous power. So hardware uses something called the interrupt. And so basically, an interrupt is a stop what you are doing right now, and something important happen. Interrupt is a stop which what are you doing right now and something important will happen. Here is the step by step flow actually, how to hardware to CPU resume the previous execution. First is a hardware sends a IRQ. We understand just what is exactly IRQ, and the CPU possesses the current execution. CPU possesses the current execution, and CPU save all the register state, and CPU check the IDT. Here initially IRQ, and IRQ possess, or the CPU possess the current execution, and CPU save all the register state. Save, here is a CPU save all register states. I will increase the, and the next CPU check the check IDT, and next CPU jump to the ISR handler. ISR handler jump jump ISR handler, and ISR processes the event, and CPU resume the previous execution. This ISR attain or the processes the event, and the CPU resume the previous execution. It means to understand this, we take an example. Here is a keyboard which having the IRQ1 and PIT IRQ0. This this uh, this interrupts will happening, goes to the PIC, and PIC will connect with the CPU and the IDT entry, which are the jump into the ISR handler. It means the IDT is basically the hardware phone book. Here is IDT is just like a hardware phone book. The hardware phone book, the CPU receive the only number like IRQ0, IRQ1, and divide by 0, which is the exception 0. But the CPU need to know where is the actual code that handle this. That mapping exists inside the IDT. A handler function has the memory address, but x86 architecture is ancient. So instead of the storing on 164-bit address directly, the CPU split into the two pieces. Think of it like the first 16 bits, then middle 16 bit, and then upper 32 bit. Together, they build the full address, which is the 64 bit. First 16 bit, then second 60, there is a middle, is also 16 bit, and the upper of this 32 bit. It so basically selector which code segment should this tells to the CPU. This tells to the CPU which code segment should I use. It points to the GDT. It points to the GDT global descriptor table. Without this, the CPU will not know whether it is running. It can be kernel code, user mode, user code, or the invalid memory. To understand this, GDT versus IDT, a simple understanding. GDT is the where to go, and IDT is the where to go, and GDT is the what permission exists there. Here is a type in program. We use the type attribute. It means this is like a security gatekeeper, which is the important bits. We present bit if this is not a set and CPU crashes because the handler does not exist. In this OS, we use the privilege level, which can control who can trigger the interrupts. Example, ring 0. It is only kernel only, and ring 3, which is user application allow. And then get type, which can define the interrupt behavior. Get type, which can define the interrupt behavior. It means usually 0xe, which is equal to the 64-bit interrupt gate. So to understand this, when hardware interrupt the CPU immediately save RIP. It means registers like the RSP, RIP, RX, RBX, flags, and many more. So why? Because after handling the interrupt, the CPU must continue exactly where it stopped. So CPU need to save the registers. Here, to understand the next part, which is the exceptions versus IRQs. It means exceptions are basically from 0 to 31. These are the CPU problems. Exceptions are from 0 to 31, which are the CPU problem, like the divide by 0, invalid opcode, then page fault. The CPU itself is panicking. And then IRQ, which are from the 32 to 47. These are the hardware signals. Example, timer tick, keyboard press, mouse movement. Hardware is asking for the attention. Here in program, we use the while one ASM halt. What exactly meaning of this? This freezes the machine forever. Why? Because continuing execution after the corruption is dangerous. This is called the safe failure. So instead of the corrupted continuation, this is very important operating system philosophy. It freezes the machine forever just because of the continuing execution after the corruption is dangerous. This is called the safe failure. And the PIC, which is a programmable interrupt controller, this is the also known as the most confusing concept for the beginner, because think of it like the receptionist. If you do not send the PIC thing, the CPU is still busy. If it means if you do not send the IRQ, like in program we will use the IRQ, just similar like that, the CPU still busy, and then no more interrupt arrive. Your keyboard stop working, your timer stop, the OS feel dead. This is a single line critical. And the PIT is a programmable interval timer. It's a heartbeat of this. So PIT is basically hardware clock. It continuously generates the interrupts, usually 100 times per second, 1000 times per second. Every tick means the time move forward. So understanding the programmable interrupt table, suppose 1193182. What exactly this number? This number is a frequency. It means 1.9 megahertz. Comes from the original IBM PC hardware from the 1981. Modern computer still emulate it. That's how the deeply backward compatibility matters. We will use in our code to understand the PIT and the divisor. Divisor is basically 1193182 divided by 100 is a basically hardware. Here is a hardware frequency, and this 100 is a desired frequency. Desired frequency. So dividing after that, each the PIT counts down from the number repeatedly each time it reaches to the interrupt. Here we use the function which is the outb. Outb is basically this sends the command directly to the hardware. Sends the command directly to the hardware. Think of ports as a tiny mailboxes connected to the physical devices. Why the PIT matter? Without the timer, your OS cannot measure the time, schedule task, sleep process, multitask, animated or anything. The PIT is literally the heartbeat of the operating system. It means the keyboard sends the scan code, not the letter. Example: when a key A press, anybody key press the key A, it will send the 30, and then OS must translate to small a using the lookup table. So before the interrupt, your OS was passive. After the interrupt, your OS become the reactive. Alive the response and real. This is the moment an operating system stop being the just code and start becoming the living machine. So just revise the all terminology. IRQ is a basically interrupt request from the hardware. ISR is the interrupt service routine, which is the actual code handler, and then PIT is a hardware timer heartbeat. IDT is a maps the interrupt handlers, and GDT is a define a memory permission and privilege level. We will start with our module one, which is the interrupt descriptor table, and this module we will write inside the include folder of kernel. And we can give the name of this file, which is the idt.h. Basically, this is a hardware phone book. It tells the CPU where to the jump when something is happening. It means struct, start with the struct, idt entry, interrupt descriptor tables entry, start with this, and initialize the uint ct and offset low, which is a lower 16 bits of the handler address. And uint16t selector, between code segment selector having the address 0x08, which is for the kernel, and one of the 8-bit uint8t, which is the IST. It means interrupt stack table used for double faults. and type attribute, type pattern, which can type and attributes like present date, then DPL, then get type, then uint16t, which is an offset middle. It means middle 16 bits of handler address. Uint 32-bit offset low. Then initially we initialize the middle in the 16-bit and high in a 32-bit. Which can upper 32 bits of the handler address. Reserve, it means it can reserve for the CPU. The attribute tag. It means what is exactly this uint offset low in 64-bit mode, an address in the 64 bits long, but x86, which can architecture is a legacy architecture, is a hardware expect the address to be the split, which can store in between the bits 0 to 15. And there is a U16 selector, which is our code segment. It means this points to an entry in our GDT. What is the GDT? Basically, global descriptor table. It tells the CPU when interrupt happen, switch to the kernel code segment. And without this, the CPU wouldn't know if it's running C code or the garbage. And then next is our 8-bit, which is a type attribute. It means the bit 7, the which can is the gatekeeper. If the bit 7, the which can is the present must be 1, and 6 to 5, which is a privilege, it means 0 0, which having the kernel mode only, and 1 1, which is having the user app scan trigger, and bit 3 to 0, which is a gate type. It means 0xe, as something example of the address, which is a 64-bit interrupt gate. And here is the offset middle or the offset high. This store the bits 16 to 63 of the address. We use three fields because the 64-bit identity entry was the retrofitted onto the old 32-bit format. Okay, we will save it and start with our another module. Save it and start with our module 2, which is the emergency room. It means the dispatcher, it received the interrupt and decide who to call. It means we start with a uint. Currently we are in the 64-bit processor, so 64T, and ISR interrupt and handler, interrupt service handler, and struct interrupt frame, star with the frame, uint 64-bit RSP, which is equal to the it means if a frame is less than 32. Where is the exceptional handling? Means the CPU is panicking. On the VJ, we will print at that condition. Call the VJ print and kernel panic and VJ print the error message, which is the exception. Except this key should be small. Exception messages and frame int number, then while win1 ASM halt this stuff, which is the freeze the machine. Freeze the machine. And else if frame is greater than equal to 32 and frame int number is less than 48, then IRQ handling hardware is calling. You int in 8-bit the IRQ, which is equal to you int 8-bit frame int number then minus 32. And if frame int number, which is 32, it's called PIT handler. Else if frame int number, which is equal to 33, keyboard handler. Then PIC EOI is a IRQ. It's basically end of the interrupt. And return to RSP. What exactly in this model do? We check in the line by line. Here is the first is a interrupt frame. It means when the interrupt occur. When the interrupt occurs, the CPU at assembly stops. It means push every register like RAX, RBX, RIP, etc. onto the stack. This stuff let's see the exact state of the computer the moment it was interrupted. And here is a frame int number is less than 32. It means these are exceptional. The CPU encounter a problem it couldn't solve, like the dividing by 0. Okay, we call this the kernel panic. And while one, it means we stop the machine in like the in infrastructure we prioritize the safe failure over the corrupted continuation. And here is a PIC UI. It means the master stroke. This programmable interrupt control is an old chip that manages the queue. If we don't send the end of the interrupt, which is AOI signal, the PIC thinks we are still busy and we never send another signal. Here is our module 2 is completed. We will save this code and start with our module 3, which is a heartbeat. It means the PIT is the clock of the motherboard. It ticks the frequency of 1.19 megahertz. We'll understand the code one by one. We write the new file for this, which is a pit.c. Inside the pit.c, we start with a void pit init and uinit 32 underscore t frequency and uinit 32 divisor, which is 1193182 divide frequency, which is our 1.19 megahertz, and out be 0x43 and 0x36. It is our command bind, which is a mode 3 where and out be 0x40 uint 8-bit and divisor and 0 and ff is a low byte. Then out be 0x40 uint 8-bit divisor greater than 8 and 0x ff. Okay, it is clear correctly. And it is our 5 byte. Understand the initially here is a number 1193192. It means this is not actually a random number. It is the frequency of the critical oscillator on the original 1981 IBM PC. Every modern computer still simulates this frequency for the backward compatibility. And here is a divisor. If we want to the 100 ticks per second, it means 100 hertz. We divide the 1.19 megahertz by 100. This result is the countdown value. Is the basically countdown value the hardware uses. And here is the outB 0x43 and 0x36, which is the command bind. It means we talk to the port 0x43. We tell the timer operate in a square wave mode. This means it will tick, reset infinitely. And last is a PIT handler. It means every tick we increment a counter. This counter is the source of the truth for the time in the OS. Save it and start with our last but not the least module, which is a keyboard module, which is a touch of the reality. Keyboard.c, start with a file name keyboard.c and void keyboard handler keyboard handler, and you int 8 underscore t scan code is equal to INB. Inside is 0x60, which can read the byte from the port. And if scan code at 0x80, it means bit 7 is set key release. Else the character C, which is equal to KBD keyboard is used, and scan code, it means map the number to letter. Then if C, which is the shell input, let's complete it. Send to the shell. To understand this keyboard.c, initially we start with the INB 0x60. It means port 0x60 is the mailbox for the keyboard. When keyboard raises and the interrupt, which is the IRQ1, it leaves 1 byte in the mailbox. Another is a if scan code. The keyboard sends the 2 signal for every key. Keyboard send the 2 signal for every key. One when the press, one when a press, and one when a release, which from the plus 128 to the value. We ignore the releases for now to keep the code simple. And another is a KBDUS, which can the scan inside the scan code. The keyboard doesn't send the letter capital A; it sends the number 30. It means we use the lookup table to translate 30 into a ASCII character, which is a. So at the end of this episode, we have a map the silicon, started the heartbeat, and opened the eyes of the machine. It means this OS is no longer just a program; it is a living entity. In the next episode, we introduce the multitasking, the ability to this heartbeat to switch between multiple threads of the existence. So the stay deploy. Let's save it.